Welcome to RaWMachines, your journey to explore the world's most impressive industrial processes. Amidst the massive scale of global commerce, there is a hero quietly carrying billions of tons of goods every year: the wooden pallet. How can humans transform rough tree trunks into millions of consistent, durable, and sturdy pallets? Join me as we delve into modern factories to better understand the process of creating this essential material. To understand the timber industry, we must start in the forest, the home of the super pine, a species that symbolizes the American spirit. In the 19th century, Mississippi, Alabama, and Georgia were once three of the world's largest lumber centers. But after that, the forests were cut down so quickly that within a few decades, many once lush areas became barren.
Right on.
But Americans did not accept the loss of their forests. Instead of letting nature regenerate on its own, they sought to regenerate it faster, better, and stronger. By identifying genes, wood density, and disease resistance, scientists created true athletes of the forest world. The super pine, loblolly pine, grows up to 40% faster than its ancestors. Instead of waiting 50 or 60 years, these trees can be harvested after just 25 to 30 years, less than half a human lifetime. Maximum growth, optimal disease resistance. It is proof that humanity not only exploits resources, but also uses science to multiply its abundance, ensuring this forest legacy will thrive forever. The super pine has completed one growth cycle, but its journey is just beginning. Now, these giant logs will be transported to the Magnolia mill, where man and machine will write the next chapter for this precious resource. This mill belongs to the Weyerhaeuser Corporation, founded in 1900 by Frederick Weyerhaeuser, who was once called the Timber King by the press. This is more than just a mill. It is a technological fortress. It is the convergence point of traditional craft and the most sophisticated technology. This facility alone processes enough wood for approximately 40 new homes every day, equivalent to about 200,000 board feet of lumber. This level of capacity and precision completely surpasses any sawyer of the past. The new life of the timber begins at the log yard. Massive southern pine logs, up to 40 feet long and 24 inches in diameter, are stacked in piles. They are not just piled randomly. Today, GPS guidance equipment and scanning technology help sort them by species and size, ensuring that each log enters its most optimal processing path. The real marvel begins when these logs meet the mill's primary analysis system. The enormous machines roar to life. The twin-band head rig slices through the 24-inch thick logs like a hot knife through butter. Each saw blade is 12 feet long, spinning at a speed that the human eye cannot fully perceive. But to achieve this speed and reliability, the technology has undergone 150 years of arduous engineering evolution. In 1808, an Englishman named William Newberry conceived of the idea for a bandsaw, a blade moving around two flywheels. At the time, the idea was deemed too dangerous and impractical due to maintenance difficulties and frequent breakage. However, nearly 40 years later, Anne Pauline Crépin proved the opposite. When manufactured with refined steel, the bandsaw was not only safe, but also many times more efficient. From there, this technology spread across North American sawmills. Each generation of engineers added a piece to the puzzle, improving blade tension, optimizing flywheels, reducing vibration, and increasing speed. Today at Magnolia, that legacy has reached a state of near perfection. Each log passing through the system is analyzed and cut individually, as if an invisible craftsman were executing every saw cut. This is a testament to the precision of technology in the new age. After leaving the twin band head rig, the cants are transferred straight to the gang saw area. The gang saw operates on a simple principle: one cut, multiple products. Instead of having to saw individual boards one by one, this system simultaneously cuts multiple boards from a single piece of wood, increasing productivity tenfold. A laser scanning system monitors the cut surface, sending data to the central software. There, an algorithm compares the actual board dimensions with the cutting pattern, calculates the deviation, and then automatically fine-tunes the speed of the next saw blade. After leaving the gang saw, the cants have taken a standard shape. However, the edges are still rough and coarse. To turn them into industry-standard products, a final refinement step is needed: edging. Its job is to remove excess edges, creating parallel faces. At speeds exceeding 1,000 feet per minute, a deviation of even a fraction of a millimeter can lead to the entire board being rejected. Therefore, the entire system must be controlled by optical positioning sensors to ensure the saw blades always follow the precise, pre-calculated path. No two boards are exactly alike, and this is where the intelligence of technology truly shines. Sophisticated optical grading systems scan and classify each individual board, analyzing the grain, knots, and structural characteristics to determine its final use: structural lumber for house framing or appearance-grade boards for interior trim. More importantly, Magnolia permits nothing to be wasted. In the recycling area, materials are divided into three main streams. Large wood chips are sold to paper mills, where they are pulped and turned into printing paper, cardboard, or recycled paper products. Fine sawdust is compressed into biomass fuel pellets, a clean energy source used for heating and power generation. Bark is processed and used as landscape material, ground cover for gardens, parks, and even children's playgrounds. This is the spirit Americans call waste nothing, want nothing. Magnolia operates as a self-contained machine. Trees grow from the earth, pass through the mill, and return to life in many different forms. That circle is unbroken because everyone in the line understands that. A seed of wood today is the shade of tomorrow. The entire system functions as a closed-loop circulatory network where every byproduct has value. This is what helps Magnolia achieve a wood utilization efficiency of nearly 100%, a number once considered impossible in the lumber industry. Now we move to the stage that determines the future quality of the board, drying. Small stickers are stacked between the layers of wood to ensure uniform air circulation. The entire pile of lumber is then moved into an industrial kiln drying oven, where the moisture content is reduced to the standard level of 10 to 15%. This process allows the wood to achieve the necessary structural stability and durability before being put into production. Leaving the kiln, the wood advances into the planer mill. High-speed blades will plane all four sides smooth, resulting in a sleek surface and precise dimensions, transforming the raw material into a finished commercial product. After passing through the most rigorous stages of technology, the boards are ready for the final step: packaging and shipping. Each board is stacked automatically by a robotic coordination system. When a bundle of lumber reaches the required count, an automatic steel strapping machine tightens around it, securing the block of wood into a sturdy unit. The strap is clearly printed with the batch number, production date, wood grade, and shipping destination. This data is simultaneously stored in the central management system, allowing for the traceability of every bundle from the forest where it was harvested to the kiln and saw lines that processed it. The lumber bundles are now ready to be loaded onto trucks, much like a well-disciplined army before deployment. From here, the journey of the forest wood concludes within the mill, and a new journey begins in human life. Next, we turn to the story of the American Northwest, the land of mountains, glaciers, and the renowned Douglas fir forests. Here, a new chapter in the U.S. lumber industry has been written: engineered lumber. If Magnolia represents the power of traditional sawmilling, then Boise Cascade is the image of innovation, where wood is no longer cut from a tree trunk, but is designed, restructured, and transformed into the material of the 21st century. This story begins after World War II, when the world needed lighter, stronger materials to build faster. Aeronautical and construction engineers realized strength comes not just from the material itself, but from how the material is organized. And that very thinking gave birth to an invention that changed the construction industry: the I-joist. From the shape of industrial steel beams, a wooden version was created. Two load-bearing flanges on the top and bottom, connected by a thin but strong web made from OSB, oriented strand board. It is half the weight of conventional lumber, yet offers 50% greater strength. The I-joist ushered in a new era, where wood could reach greater spans in large structures while simultaneously conserving forest resources. This is a testament to the extraordinary adaptability of American industry, especially the company Boise Cascade, in turning natural limitations into technical advantages. Now, let's move on to the most fascinating part: how an I-joist is made. One, drying. The journey begins in the veneer drying area, where paper-thin wood sheets are sent into a massive recirculating heat chamber. Inside, hot air at 200 degrees Celsius blows through narrow vents, removing moisture layer by layer. When the veneer exits, its surface is smooth, dry, and has only about 6% moisture, perfect for bonding with phenol glue. Two, flange production. The dried veneers are sent to the layup and pressing section, where they are turned into LVL, the flanges that form the top and bottom of the I-joist, and the parts that bear the most load. Each veneer layer is coated with phenol formaldehyde resin and stacked with alternating grain directions. On the conveyor, the layers form a massive sandwich, dozens of sheets thick. Once the stack is ready, it's moved into a hot press where the temperature reaches 170 degrees C. The glue melts, penetrating each wood fiber and bonding everything into a single, solid block. Afterward, the LVL planks go through a grooving machine to create slots that perfectly fit the OSB web. Three, web production. Next comes the web of the eye joist. Thousands of long wood strands are oriented parallel to each other, mixed with resin, and compressed into large flat sheets. OSB provides excellent shear strength, a stable surface, and lightweight workability. It's the perfect layer to connect the two LVL flanges. 4. Assembly. Finally, both components come together. The LVL flanges are aligned in parallel, the OSB sheet slides in between, and the entire assembly passes through the radio frequency bonding system, a process that uses electromagnetic waves for adhesion. At this stage, high-frequency energy passes through the glue, causing the molecules to vibrate and generate heat from within, curing the adhesive in just a few minutes. 5. Cutting and final inspection. Once the beam exits the press, it's cut precisely to standard lengths, 8, 12, or 16 meters, depending on project requirements. Each finished joist is then scanned with ultrasonic sensors to detect hidden defects within the glue line or veneer. Those that meet quality standards are printed with a tracking code, coated with moisture protection, and stacked on pallets, ready to ship to construction sites across North America. Each eye joist is the culmination of multiple levels of engineering, from forest biology, adhesive chemistry, radio wave physics, to production automation. Above all, it demonstrates the mindset of restructuring natural materials to serve modern needs, lighter, stronger, and more resource efficient. At Boise Cascade, they often say, "Wood is good enough. Our job is to make it smarter." That statement encapsulates the spirit of the entire mill, where humanity no longer just exploits nature, but engages in a dialogue with nature through the language of engineering. Leaving the United States, the journey of wood continues across the Atlantic to southern Germany, the headquarters of Möringer and Lagenbau. Following World War II, with the country in ruins, the Germans chose the path of revival through quality. They could not manufacture cheaper, but they could manufacture better. From that philosophy, German quality became a source of national pride, and Möringer is a direct product of that spirit, a business that has transformed woodworking machinery into an art of precision engineering. After just 20 years, Möringer had become a symbol of fine European wood engineering, exporting machinery to Sweden, Canada, and the US. One, laser scanning. The first technology that defined Möringer's name was the multi-layer laser scanning system. The log is fed into a scanning chamber, where dozens of laser beams shine across its surface, creating a 3D model accurate down to the millimeter. This technology is similar to the CT scan system in medicine, but instead of reading the human body, it reads the body of the wood. Two, cutting. Next is the combined system for parallel cutting and edging. Here, instead of moving through multiple saw stations, the entire process is unified. The log is rotated, positioned, and cut into multiple faces in a single pass. This technology not only reduces processing time, but also maintains absolute parallelism between the edges, a key factor determining the final product quality. Thanks to these improvements, production lines using Möringer technology achieve an average error rate of under 0.1%, a number that was once almost unimaginable in the wood processing industry. But what they are most proud of is not the precision, but the repeatability. Every shift, every day, every year, the results are always the same. Möringer's technology has transformed machinery from mere tools into partners for the craftsman, able to see, understand, and make decisions like a true master. In this world, the boundary between mechanics and knowledge fades. Only the art of precision remains. In the final stage, each board continues to move to the end trimming area. Here, a series of high-speed circular saw blades are arranged horizontally. Laser sensors scan each board, measure its length, and then issue the cutting command at a predetermined position. Afterward, the automatic sorting system, using pneumatics and paddles, directs each board into its appropriate group. When the final standardized boards are stacked, we can see a neat warehouse, where hundreds of thousands of boards are normalized, each one carrying its own unique identification code, traceable by its origin, dimension, and quality. That is the epitome of modern manufacturing, not just creating products, but also managing all their data, from the forest to the mill. And so, our journey concludes, from the monumental mills like Weyerhaeuser's Magnolia, to the Boise Cascade plant, where humans no longer just saw wood, but redesign it, and finally to Möringer in distant Germany, where precision is elevated into a life philosophy. 3 locations, 3 approaches, but a single common thread: the evolution of the timber trade, from manual labor to machine intelligence, from instinct to science, from natural material to a technically reborn material. All 3 form a panoramic picture, the path of evolution for the 21st century wood industry, where every saw cut, every board, every algorithm extends the enduring relationship between humanity and the forest. Wood has never been merely a material. It is a memory of time, a witness to labor, the foundation of civilization. Each annual ring tells a year of sun and rain, and every wood product tells a chapter of human history. From the first small cabin in the Wild West to the modern high-rises soaring above major cities. Today, as the world moves towards sustainable development, wood once again stands at the center, not only because it is a renewable material, but because it symbolizes the balance between nature and technology. 2 elements humanity is striving to reconcile, and it is companies like Weyerhaeuser, Boise Cascade, and Möringer that are proving it is possible. We can manufacture, build, and develop without losing our bond with the forest. As we leave those mills, the roar of the saw fades, leaving only the rustle of the wind through the pine canopy. A cycle closes: forest, human, machine, and back to the forest. In that cycle, we see the deepest legacy the American wood industry leaves the world: a legacy of respect. Respect for the material, respect for the labor, and respect for the life within every wood fiber. Because wood is not only something humans create, but something that helps humans remember where they came from nature, and will forever be connected to nature, no matter how many new technological eras the world enters. Thank you for listening to the end of the story. If you also enjoy similar videos, please hit the like button, share, and subscribe to the channel so you don't miss any fascinating stories to come. RaWMachines says goodbye, and see you next time.